So we discussed about different tasks in previous last session and at the beginning of this session that we deal with when we talk about graphs. And now we go back to the node level tasks and edge level tasks and see what methods we use to solve this type of problems. So the idea before deep learning, basically, like before in the past 20 years, or I mean 15 years, for example, deep learning has been 10 years even. Deep learning has been very much in use everywhere, but before that, people were trying to apply machine learning algorithms and learn as well. So the idea was that they essentially found or designed mathematical methods to extract features on different levels of graphs without any learning. So essentially deterministic methods that don't have any parameters to learn, and based off of some formula, they got to the features. So these features are still being used even in current deep learning models. Some of them are very competitive with current models, and some of them are generally basis for the current approaches. So when we deal with a graph, we can describe its structure fully just by saying what type of connections it has. So we have the adjacency matrix, essentially. We know what nodes are connected to each other, and that will give us all the information that we need to about that graph. But usually we deal with large structured data, and it is really hard to learn something on a graph, for example, that has 1 million nodes. For example, you have web pages in an internet, basically web graph, and it's really hard to learn anything on that graph of just a combination of all the nodes. If you have a small graph, your eye might be able to detect, okay, there's a cluster here, but that's also a qualitative measure, it's not quantitative. So it is the best if we can come up with, I mean, it is the most natural thing to come up with some measures to be able to characterize nodes in a graph. So that's the idea that we're starting with here. And we will first start with the node level. So nodes, let's look at this graph. This graph is called Florentine families graph. It's essentially each node is representing a family in Florence in a few hundred years ago. And these connections show marriages between the two families. And sociologists were using this type of graphs to analyze many things. For example, in past times, marriage meant political power. So people just got married so that those two families basically they have more political power. So studying these type of graphs were essentially equal to studying some basically the politics at that time and era. So sociologists designed this graph, and they wanted to come up with measures of importance of different nodes in the graph and see how important some family was based off of their connections, based off of the marriages that they had with each other, basically family connections. Now, the idea is that we want to come up with some measure that shows how central a family is, how important one family is. So the natural idea, the first idea that comes to mind is degree. We see how many families one family is connected to. All right, so let's define that. Degree centrality is essentially the total number of neighbors that the node has. When we have an adjacency matrix, it's essentially the sum over rows or columns of that, because this is undirected graph. It is going to be symmetric adjacency matrix, and then the columns and rows are going to be essentially equal to each other. For example, let's think about a group of friends. One of them, which has more friends, basically is closer to everyone, is more central to that group of friends. Not everyone might be, friend with each other, for example, in this class, but one that is friend with more people probably will be, if he had some idea, people, will hear his idea more, and so on and so forth. Same goes, so that's from about undirected graphs. You have citation graphs as well. A paper that is cited a lot of times, it means that it is an important paper, probably, most likely. And so it's a fair logic to assume that a node that has high number of neighbors is also an important. But that's not always the case. Let me tell you that I have one friend. Then you would say, in a group of friends, so I'm talking that I have a friend, and you're saying, oh, okay, he only has one friend, so he's probably not that popular or not that influential. And then I tell you that one friend of mine is US president. So everyone is like, okay, he is probably an influential person because, he is friends with some important guy. So it is fair to say that not only we should consider the number of neighbors that a node has, we should also take into account how important those nodes are. So it is fair to say that someone can be influential by just being friends with a lot of people, being connected to a lot of people, or being connected to few influential people, right? So that's the idea with this type of centrality. We call it eigenvector centrality, and we will see shortly why. So let's formulate this. For each node I, we say that we call it centrality EI, and we say that it is proportional to the sum over all the neighbor nodes of VI, sum over all importance and centrality of those. Right? So centrality of each node is equal to sum over all centrality of all its neighbors. Now, I don't like this type of sum. I want to get rid of this. I will write sum over all the nodes in graph and then multiply that with the adjacency matrix element. So what then basically will happen is that if I and j are connected, this guy is going to be 1. If they are not connected, this guy is going to be 0. So there is no need to define basically the sum over neighbors anymore. So we define sum over all the nodes in that graph, and we write that in matrix form. It is going to be this way. A is a symmetric matrix. It is a square matrix. So it has, but it doesn't have one eigenvector or eigenvalue. For example, let's say that we have n nodes. This A is going to be n by n, and it's going to have n eigenvectors, n unique eigenvectors. So what happens now is that, which one of these eigenvectors should we select? So E, essentially our centrality, now shows itself as an eigenvector. And we want to show importance with positive numbers. We don't want to go negative. So if we want to select a vector, an eigenvector that has all positive elements, it's going to be the eigenvector corresponding to the leading eigenvalue. And there's a theorem that basically this comes from. Because the adjacency matrix is essentially positive, basically all elements on the adjacency matrix is non-negative, and it is a square matrix. So what happens is that based off of Perron-Frobenius theorem, all the elements on the leading eigenvector are going to be non-negative. And we're going to select that as our centrality. So eigenvector, the leading eigenvector has n, basically its dimension n, and each element in that eigenvector represents the centrality for the corresponding node in that graph. So we go to Florentine family's graph again. We see that these two nodes, who each of them have 4 neighbors, right? These two nodes. This guy, in previous measure, degree basically centrality, had higher importance. This node now, all right, sorry. So in degree centrality, both of them had the same centrality and importance. But now, since this node has a neighbor that is of low importance, it doesn't have much neighbors or connections to any other node except for this. We see that this guy now, based off of eigenvector centrality, has a higher centrality.